Greetings to all. The session is regarding intermediate chemistry. We'll be fetching for your international competitive exams and entrance exams as well. India level JEE Advanced, JEE Mains, that will be giving the way into admissions into IIT, NIT technical stream. NEET chemistry will be entrance will be conducted all across India. That is for medical entrance examination. In addition, Telangana government and Andhra Pradesh government are conducting MCET examination for engineering entrance. So all these exams where the chemistry content will be there, this kind of session will be helpful. In addition, government is organizing government jobs, career opportunities, where general studies is the common question paper you can find. So that can be combined with the various sections of sciences. Among all, chemistry is the prominent one where you can find the content which is helpful what we are discussing now. Let's enter into our today's session. What is the name of this platinum NH3 taken 4, platinum Cl taken 4? As per the IUPAC protocol, we have to assign the name for this double complex. Why we are saying double complex? Here, one of the complex pair you can notice for platinum, ammonia. In either pair you can notice for platinum, chlorine. So that this complex naming as per the IUPAC protocols, we have to assign. Let's see. Here, ammonia is said to be neutral ligand. So that first complex where the platinum complex with the ammonia can be taken into the consideration. Whereas chlorine is always assigned with the negative one charge, which is making the complex as an anion. Therefore, ammonia containing platinum complex is the first one, followed by chlorine containing one will be there. So that the IUPAC nomenclature coordination compound naming is tetraamine. How many amines you can find? Tetraamine. Here, tetraamine for what? Platinum. This tetraamine platinum can be taken. So, after this, in the Roman numeral, you mentioned with the 2. 2 indicates what? Oxidation state around the central metal. Right. So here, platinum actually not having any charge in consideration with this ammonia, right? Ammonia is a 0 oxidation state always. But how can we give +2 over here? Because in the entire complex, chlorine is always having -1. If you count all the negative charges, 4 can be multiplied with -1. So that -4 charge for the total complex. But total complex is having 2 platinum metals. So that they counterbalance the -4 with the +4. +4 can be shared among 2 metals. No, that's why platinum 2 accorded for first platinum and platinum 2 for second as well. So that we are going to share the charge in this manner. In this way, tetraaminoplatinum 2 is of one complex and being it is a cationic with respect to the second one, so that second complex is mentioned with the 8 as the suffix. So how many chloro are there? You can notice 4 chloro around the platinum. Being it is the complex accompanied by the positive charge over here, so that second platinum is designated as a platinate. Again, we have to give the charge of +2, right? The entire name of the given double complex as per the IUPAC protocol, tetramine, platinum 2, tetrachloroplatinate 2. This is the way naming will be assigned, where we have to go for neutral ligand first priority, so that this platinum complex of first and this platinum complex of second being negative ligands are associated. Tetramine are accompanied with the tetramine platinum, so that total positive charge can be distributed among 2 metals, so that platinum 2 and tetrachloroplatinate 2. This is the way naming is provided for question number 1. Move on to question number 2. Question number 2 is taken from organic chemistry, and this is the compound where dicarboxylic acid you can notice. It is a part of dicarboxylic acid and named as a malic acid. Malic acid where you can notice 4 carbon length chain in the Fischer projection, and 2 terminal carbons are accompanied by acid functional groups, and second carbon is having OH and third carbon is CH2. The question is, on the structure, draw a circle around the alcoholic functional group. Alcohol stands for hydroxyl. Hydroxyl, how many are there? If you see, here is OH, here is OH, here is OH. Most of the people will will have the misconception that these many OH are present, so that we can go for 3-hydroxyl in this. But it is the wrong conception. But the thing is, only this is considered as a hydroxyl, and this is entirely considered as a carboxylic acid. COOH, all together carboxylic acid. Here also COOH, all together carboxylic acid. Hence OH is only one, that is this second carbon OH is the one. And the second question in this category is, deduce the formula of malic acid to show number of carbons, hydrogens, and oxygen atoms. In the given molecule, so in order to write its molecular formula, first of all, we have to count the number of carbons. 1, 2, 3, 4. C4 we can designate, and oxygens to be taken. 1, 2, 3, 4, 5. O5, C4, O5. Hydrogens, let's count hydrogens over here. 1, 2, 3, 4, 5, 6. H6. So entire molecular formula is C4, O5, and H6. This is the way all the questions got answered for malic acid, and it is simply a biomolecule with the dicarboxylic acid on the terminal carbon atoms and one of the hydroxyl on the second carbon. So here all the questions got perfectly answered over here. For question number 2, hydroxyl are only one, and molecular formula will be C4, O5, H6. Move on to question number 3. Question number 3 is collected from JEE Advanced 2018 question paper, and it is a part of Raoult's law. Raoult's law related with the colligative properties, physical chemistry part it will be. Let's read the question first. Later on we will go for how to solve this one. For a solution formed by mixing liquids of L and B, two different liquids were taken. One is L, one is M. The vapor pressure of L plotted against the mole fraction of M in a solution is shown in the following figure. Vapor pressure of L was taken on the y coordinate and mole fraction of M taken on the x coordinate. This plot was given over here, where you can find the curvature. Here, XL and XM represent mole fractions of L liquid and M liquid respectively. Here, mole fraction can be taken for two different liquids in the solution. The correct statement applicable for this. So if you go for our application of Raoult's law for this given components, what will be the correct statements, right? For question number 3, the expected answer should be attractive intermolecular forces between the liquid L and liquid L in the pure liquid L and liquid M in pure liquid M are stronger when compared to the liquid L and liquid M. When we are going to take pure forms of L liquid and M liquid, the forces of interactions are stronger. Whenever L liquid got mixed up with the M liquid, what happens? They used to minimize the forces of interactions among the two liquids. That will be the correct statement regarding this graphical representation. Let's see how can we explain, right? For the given condition of mixture solution, we have to consider mixture solution. L liquid got mixed up with the M liquid. Whenever mixture solution was taken, the graph of vapor pressure against the mole fraction was given. So vapor pressure taken on y coordinate and mole fraction taken on the x coordinate. Whenever these two liquids, L and M liquids, are taken into the consideration, the curvature is obtained that is provided within the question only. Within the question only, you can notice this graphical representation, curvature you can notice. But in practical sense, Raoult's law for the given ideal solution is like a cross, right? So this is a kind of Raoult's law. Raoult's law is moving in this direction with a positive progress, and here in either negative progress you can notice for mole fractions of A and B liquids. If they are perfectly obeying Raoult's law, this is the way graphical representation can be noted, and that is also mentioned in this with the dotted lines. But whenever you observe the actual practice, we got the curvature above that dotted line curve. So this indicates what? In the figure, it is clear that Z point shows the vapor pressure of pure liquid. Z point. At this point Z, what you can note is vapor pressure of pure liquid L. Not the liquid. Only this is for what liquid L, vapor pressure is indicated on the Z point. Okay. Then mole fraction of L is equal to 0 to mole fraction of L is equal to 1. Mole fraction L is equal to 0 to mole fraction L is equal to 1. This entire region is taken into the consideration, right? It is obeyed when XL tends to 1. Whenever mole fraction of liquid L tends to 1, then only this kind of positive deviation can be applied. This is said to be a positive deviation, which is mentioned over. This graph clearly represents what? Whenever we are mixing liquid L with liquid M, the forces of interactions are becoming weaker. So weak forces of interactions can be noticed. But in case of pure liquids, the forces of interactions are very strong in nature. So this is the way the option number D is exactly prominent for the given question. Move on to question number 4, and again it is collected from JEE Advanced 2018 question paper. The correct statements about the oxo acids of HClO4. HClO is R. HClO4 is oxo acid of chlorine, and this HClO is also oxo acids of chlorine. So this is the question collected from what inorganic chemistry in specific. We can say groups can be taken, and this is the element. Chlorine is the element related with the 17th group, halogen family elements. So we can go for HClO4 and HClO. HClO4 is called perchloric acid. HClO is called hypochlorous acid, right? Whenever these taken into the consideration, what are the exactly correct statements about them? Are here, the central atom in both HClO4 and HClO is of sp3 hybridized. HClO4 is more acidic in comparison to HClO because of the resonance stabilization. HClO4 is formed in the reaction with the chlorine and water. The conjugate base of HClO4 is weaker than H2O. In order to answer which are the correct options among all the given, we have to go for the explanation part. The structure of oxo acids are provided. It's a bent structure. HOCl is taken as a bent structure, and HClO4 is taken like a tetrahedral geometry. And both the structures, central atom is sp3 hybridized. Oxo acids are sp3 hybridized. Whatever they are saying, in both cases, sp3 hybridization is there. That is perfectly correct. You can put a tick mark for option A. Move on to next one. HClO4 is more acidic in nature because after donating its proton, it is stabilized by 4 resonating structures. Whenever H plus is donated, we will get oxide, O minus. That O minus is highly stabilized by resonating structures. These 4 equi-resonating structures are possible. Always the negative charge is shared among all 4 oxygens in equal manner, so that it is highly stabilized. It is a stronger the acid. HClO4 is more acidic than HClO because of the resonance stabilization of anion. That is also perfectly correct. This is explained with the resonating structures. One fundamental thing to be understood, more the resonating structures, more will be the stability for the given complex. So that all 4 are contributing the stability for HClO4. So that perchloric acid is more stable one. There is no such a stabilization in ClO minus. When you go for ClO minus, such resonance stabilization is not performed because sharing oxygens are not present, only one oxygen to accommodate that. So the charge is localized. So this will not be that extent stable. Formation of HClO4 is given as NaClO4 plus HCl gives rise to NaCl HClO4. Sodium perchlorate can be combined with hydrochloric acid, sodium chloride, byproduct, and perchloric acid will be generated. But they are saying that HClO4 is formed by the addition of chlorine and water. Direct combination, they are saying it is not at all correct. C is wrong statement, what they are provided. Go for conjugate base of HClO4, ClO4 minus, and weaker than the water in nature, because HClO4 is strong acid. Whenever strong acid is there, its a conjugate base will become reciprocal, means weak. HClO4 is a stronger acid, so that its conjugate base will be weak in nature. Conjugate base of strong acid is always weak. The reaction of this is given by whenever it is added with water, what happens? Water is stronger in comparison to perchlorate. So that the conjugate base of HClO4 is weaker than that of water. That is perfectly correct what they are saying. Always, whenever the compound itself is stronger, its a conjugate base will become weaker. So that conjugate base of HClO4 is weaker when comparison to water. This is correct. Only option C is wrong, except A, B, and D all are correct only with regarding oxoacids of chlorine. For question number 4, A, B, and D are the correct answers. Move on to question number 5. Question number 5 collected from MSET examination conducted by Telangana government in the year 2022. The aqueous solution identified the pair of ions which are colorless. Colorless ions to be identified. Scandium plus 3 and Zn plus zinc plus 2. Scandium plus 2 and Zn plus 2. Vanadium plus 2 and copper plus 2, titanium plus 3 and manganese plus 3. Among all, scandium plus 3 and zinc plus 2 are the correct answers. How can we answer this one? Let's see. Scandium is the first element of transition series, and it is the D block element with atomic number 21, can be accorded with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. If we observe, outermost valency shell is having s orbital with the 2 electrons, d orbital with 1 electron. If you discard 3 electrons, so that scandium will become scandium plus 3. They are saying scandium plus 3, right? So remove electrons from all valency shells, so that 4 is 0, 4d 0 it will be. And whatever inner shells are there entirely filled and obeying octet rule. Whenever these outer electrons got removed, 4s and 3d electrons got removed, the inner shells are completely filled. Whenever completely filled configuration is there, that is said to be what? Diamagnetic in nature, and indeed we can say colorless. So that scandium plus 3 is perfectly colorless because of lack of unpaired electrons over here. Whenever electrons are odd electrons are present, they will be excited easily. DD transitions are corresponding coloredness to the transition metals. Most of the transition metal complexes are intensified colored. That is because of DD transitions, we can say, and also ligand to metal charge transfer, metal to ligand charge transfer. This is the way colored complexes are appeared for the transition metals. Scandium plus 3 complexes are absolutely colorless because of lack of DD transition, and all the valency electrons got removed and inner electrons are completely paired up. Move on to Zn plus 2. Zinc is the D block metal, but not considered as a transition metal. Transition metal must possess at least one lone unpaired electron in that, but it is the completely filled one, so that you can designate zinc as a D block element rather transition element. Okay. 3d0, 4s0. Outer shell is completely filled. You can notice 4s2 will be there, 3d10 will be there. 4s2, 3d10, completely filled configuration you can notice. If you want to convert metallic zinc into zinc plus 2 cation, so that remove 2 electrons from the 4s orbital, so that it will become 3p6, 3d10. The outer shell is having completely filled, no odd electron you can notice, so that no DD transition occurred. So the zinc and 0 oxidation state, or else Zn plus 2 all together are said to be colorless only because of absence of DD transitions, lack of unpaired electrons over here. Such a condition may not be noticed. Scandium plus 2, if you go for scandium plus 2, is having one of the unpaired electron over here. This 3d1 electron will be there. 4s2 electron lost, but 3d1 will be there under scandium plus 2 condition, which is colored. But Zn plus 2 again, we can go for 4s0, 3d10, so that completely filled colorless only. Vanadium plus 2, scandium, vanadium, titanium. And the vanadium plus 2, if you see, what happens? 22. so that d2 electrons will, s orbital electrons will be removed, d electrons will be left. 2d electrons will responsible for coloredness of the complex, so that vanadium plus 2 is colored due to 2 unpaired electrons. Copper plus 2. Copper plus 2 is a copper metal of 29 atomic number, where S1 is there, D10 will be there. So S1, D10, if you remove 2 electrons being it is plus 2 die positive, so that S0, D9 will be. D9, 1 electron will be odd. So that you can say copper plus 2 is intensified blue color. Now the blue color you can notice. Titanium plus 3. If you go for titanium plus 3, where valency electron is accompanied by what you can say 4s2 and 3d2 will be there. 4s2, 3d2 if present, 4 electrons are there in the valency shell. Among 4 electrons, you are going to remove 3 electrons being it is a tripositive. So titanium plus 3 able to remove 3 electrons. 1 electron responsible for colored complex. So the titanium plus 3 are colored due to the presence of 1 odd electron in its valency shell. Manganese plus 3. Manganese is of D5 system, where 25 is the atomic number, so that you can find the 4s2, 3d, 5 electrons will be there. 4s2, 3d, 5. How many valency electrons? We have 7 valency electrons. Among 7 plus 3, tripositive will remove 3 electrons. 7 minus 3, you can find only 4 electrons in its valency shell. D4, it will become s electrons 2 removed. From d orbital, 1 electron removed, so the D4 system. After Mn plus 3, it will be D4. D4 is odd electron containing, no? So that you can say it is intensified colored. So you can notice colored complexes because of 4 odd electrons. Titanium plus 3 with the 1 odd electron. Vanadium plus 2 with the 2 odd electrons. Copper plus 2 with 1 odd electron. Scandium plus 2 with 1 odd electron. Zn plus 2 0 odd electrons. So colored complex is not possible. Colorless for Zn plus 2. But scandium plus 3 0 odd electrons. Zinc plus 2 0 odd electrons. Only the possible answer will be option number 1. For question number 5, option number 1 is the correct answer. Due to the absence of DD transition, they are colorless complexes. Right. Here the detailed explanation provided. No visible light is absorbed. Visible light is responsible for colored complexes. Our vision, for example, if you go for your vision, you can see all colors around you because your pupil is having tendency to notice the colors in the visible region only. If you go beyond the visible region, IR light you can't notice, UV light you can't notice. Our vision is not capable to capture the vision beyond this visible region. That's the reason why visible light, whatever colors we have, we are able to identify, we are able to see. But the complexes of scandium plus 3 and Zn plus 2 are not having provision to absorb the visible light. If they're not responding towards visible light, the colored complexes are not seen because colors are visible only in the visible region, where you can find the VIBGYOR. 7 colors are the part of this visible light, no? So that scandium plus 3 complexes are colorless. Why? Because no visible light absorbed by them. Even zinc case 3D level is completely filled, no? So that electron can't be promoted from ground state to excited state in the central zinc metal. There also all zinc complexes are colorless only. Right? All scandium complexes under plus 3 oxidation state around the central scandium, they are colorless. This is the way we can answer. Visible light is not absorbed because DD transitions are absent, because lone pair of electrons are absent in those valency shells of the identified metals. Move on to question number 6, last question of the session. How many of the following complexes are diamagnetic? Always the property of diamagnetic, paramagnetic, ferromagnetic purely depends upon the nature of valency electrons. Either valency electrons are parallel or else valency electrons are paired. Singly occupied valency electrons are causing paramagnetism. Paired valency electrons or zero valency electrons are causing diamagnetism. We have to search for all the paired up electrons or else zero electrons in the valency shell, then we go for diamagnetic nature. In order to count the diamagnetic complexes in the given options, we have to go for how many complexes are having paired electrons in that. Unpaired electrons are capable of paramagnetism, right? So here, the correct option is 3. Among given 1, 2, 3, 4, 5. 5 complexes, 3 complexes are diamagnetic in nature and the rest 2 complexes are paramagnetic in nature. The complexes belongs to cobalt as well as nickel. Nickel and cobalt complexes are provided. Cobalt is of 27 atomic number, D7 system. Nickel is of 28 atomic number, D8 system it will be. But there is a variation in the strength of ligands. Ligand strength matters for the magnetic nature, right? So weak field ligands will not pair up the electrons, rather strong field ligands having tendency to pair up the electrons. So that is the factor related with the magnetic nature of the compounds. Strength of the ligand will influence and the number of valency electrons shows the effect and what charge they are accompanied. Everything matters for their magnetic behavior. And the expected answer is 3 complexes. Let's see how can we go for their calculation. First of all, we have to go for hexamine cobalt plus 3 cation. So for that, cobalt NH3 taken 6 plus 3 inner orbital or low spin complex it will be. Whenever low spin complex you are saying, low spin always got the paired up electrons like this. Whenever all electrons got paired up like this and all 6 ligands are contributing 12 electrons are mentioned over, which is said to be due to sp3 hybridization. This is the way all the electrons are paired up and it is the part of diamagnetic. One of the complex comes under diamagnetic. Move on to second complex, hexafluorocobalt minus 3. In that case, hexafluorocobalt minus 3, fluorine is the weak field ligand. So weak field ligand, which is said to be high spin complex. High spin complex always tends to give the unpaired electrons like this. And whatever electrons coming from fluorine are 6 ligands contributing 12 electrons. So that 1, 2, 3, 4, 5, 6. 6 ligands are giving 12 electrons like this. So this is the way you can notice what sp3d2. sp3d2 outer orbital complex will be generated and though we are forming outer orbital sp3d2 complex, inner d orbital is having 4 odd electrons which is responsible for its paramagnetism. Always spinning electron used to induce the magnetic nature which is responsible for paramagnetism. But in case of paired up electrons, the rotation of positive compensated with rotation of negative, so that paired electrons give the diamagnetism. Hence, in this cobalt hexafluoro complex, 4 odd electrons responsible for paramagnetism. So it is not the part of diamagnetic. Move on to nickel tetracyano complex ion. So that here you can notice minus 2. So nickel tetracyano minus 2 charge containing species is given. In that case, it is the square planar. All 4 cyano ligands are arranged in the equatorial position around the nickel and giving the square planar nature. Square planar is responsible for dsp2 hybridization. dsp2 hybridization cyano are strong field ligands which are giving the inner orbital complex and said to be low spin complex. This is the compound called a low spin complex and all electrons, if you observe around the nickel, all the electrons are paired up. Whatever electron pairs given by the nitrile or the ligand of cyano are 4. 1, 2, 3, 4 pairs of electrons are provided. So d orbital, 1s orbital, 2p orbital. So dsp2 will be the hybridization. And after the hybridization, if you notice, all the electrons got paired up. Paired up electrons responsible for what nature? Diamagnetic nature. So that this is also the part of diamagnetic. First one and third one. Move on to nickel tetracarbonyl. Nickel tetracarbonyl is a purely tetrahedral complex. Nickel surrounded with the 4 carbonyls where inner d orbital is completely filled up and s orbitals also infused into the 3d orbital, so that all the electrons got paired up like this. D10 will be obtained because carbonyl is a neutral field ligand, will not contribute any charge over nickel. Nickel is zero oxidation state around the central metal. So that 3d8 and 4s2 system, two electrons infused inside, and it will become all paired up, and s orbital and 3p orbitals are vacant in order to accommodate electron pairs which are provided with the carbonyl ligands, so that all four orbitals got mixed up. sp3 hybrid orbitals will be generated. After the hybridization, if you observe, all the electrons got paired up, and it is the example of diamagnetic. We already noticed cobalt complex, cobalt hexamino complex, nickel tetracyano complex, nickel tetracarbonyl complex. These three are said to be what? Diamagnetic in nature. Move on to nickel tetracarbonyl negative to anion. So for that, we have to examine how the hybridization will be, how the electronic configuration will be. In case of nickel again, of 3d8 system, 4s orbital is having two electrons. Being chlorine is a weak field ligand said to be high spin complex, and electrons are not infused inside, rather two unpaired electrons, two s orbital paired electrons, and this p orbital, three p orbitals are capable to accommodate this what electrons given from the chlorine, so that we can notice four chlorines are giving four paired electrons, right? Here one paired electron, second paired electron, third paired electron, fourth paired electron. In case of nickel tetrachloride -2, here nickel is experiencing what charge? Nickel +2 will be there. Here you can clearly notice Roman numerals, it is mentioned with +2. Oxidation state +2 around the central nickel, so that two electrons from s orbital lost, right? So that it is vacant. This vacant orbital and the 4p vacant orbitals got accompanied with four electron pairs by the chloroatoms. Ligand always having natural tendency to give lone pair of electrons. So here 1, 2, 3, 4. These four electron pairs are provided with the chlorine. And these two electrons, 3d8 system, you can notice 1, 2, 3, 4, 5, 6, 7, 8. Being it is a weak field ligand, electrons are not paired up, rather unpaired electrons responsible for paramagnetic nature. So that you can't count nickel tetrachloride -2 as a diamagnetic. It is the part of paramagnetic with the unpaired electrons. So always weak field ligands gives the paramagnetic complexes. Strong field ligands gives the diamagnetic complexes. First one, third one, and fourth one are the part of diamagnetic. 3 is the correct number. For question number 3, option 3 is the correct answer. By this, we entirely completed the session with regarding to the intermediate content. We'll be fetching for your competitive exams and any entrance exams you are aspiring for. And we had a look on various sections of chemistry, and definitely it will be the informative session. And if you're curious about the discussion regarding the chemistry, definitely you will increase your enthusiasm towards learning more content in the near future. And I'm sincerely requesting to like the channel, comment which part is important, and I have a question regarding this entire session. What change in a hybridization can be noticed in between nickel tetracarbonyl and nickel tetrachloride -2? Let me repeat the question. Mention the hybridization of nickel tetracarbonyl and nickel tetrachloride -2. So hybridization question is provided. So you can put your answers in the comment section and share with the aspirants who are serious about the preparation and curious for the chemistry content. And subscribe the channel to achieve more such updates in the near future. Thank you for your patient listening. Thank you one and all.